Section 1.6, we're going to continue our discussion of limits. Last section we looked at end behavior limits, what happens on the ends of a graph. On this section we're actually going to look more about what's happening on the middle part of the graph, not at the ends. Now to start with, let's talk about what a limit is. This is a very non-precise definition of limit, just for you. A limit, conceptually, is a y value that a function approaches, but it may or may not equal. There was a movie a number of years ago called IQ. Has anybody seen the movie IQ? It has Meg Ryan in it and Tim Robbins. And in this movie, they kind of like each other. I know movies are never like that. And Meg Ryan is Albert Einstein's niece. Anybody seen this movie? Nobody. It's very cute movie. And she says to him, it's mathematically impossible for you to get from me, for you to get from you to me. Like you can't approach me. Because every time you do, you cut half the distance. And then you cut half the distance, and you cut half the distance, and when you keep cutting half the distance, you never get there. Right? Because you can always divide by 2. But you're close enough, right? You're close enough to get there. And that's what a limit is. A limit is getting close enough to get there. Now there's some notation. We've talked a little bit about this notation already. The part that's new is these values below. When we looked at it in the last section, they had infinities down there. And now we have a number. Not only do we have a number, but in the first 2 cases, we have a sign after the number, a plus or minus. So, what does it mean? Well, it means that the x value is approaching 3. So we're getting close to the x value of 3. That's fine. But this is telling you from which direction. So the plus sign means from the positive, or the right-hand side of the graph. And the negative means from the negative, or the left-hand side of a graph. And if there's not a plus or a minus after, it means you have to come from both directions. Okay? So the whole goal is to get close to a specific x value. And these symbols after it tell us from which direction. So we definitely need an example that shows it, right? Does everybody have that one written down? I see a couple people still writing. Okay, is everybody good? Yeah? All right. So my picture should match yours, at least fairly close. Sometimes the images don't quite connect to each other, so if there's a disconnect somewhere, please connect it. Yes, I can. Mm-hmm. Good? Okay. Okay, so sometimes when this prints off, it kind of disconnects this piece right here, so make sure those are connected. There shouldn't be a gap. So if there's a gap on your piece of paper, just connect it for me. So this is our image, and when we're looking at this, all of those, they're not marked on there because it's sometimes quite difficult to draw images inside of Microsoft Word. It just is not user-friendly. But this is -1. Okay, so each of those hash marks, if you will, represent number 1. So -1, this would be 1. This is -2 down here on the bottom. This is 1 and 2 up here on the top, and so forth. So every hash mark's a 1. That's all. All right, so over here on the right-hand side, up here, it's asking us to find some limits. So this one's telling us x is approaching -1, and we know where -1 is. It's right here, but we want the -1 on the graph, not on the axes. Okay, so I want to know what happens to the curve at -1. And we know from the graph that there's a jump there, correct? So if we're taking a look at that, it really matters which side of that jump we're talking about as to where we are on a graph. So on the first one, it says that we're supposed to be looking at this from the right-hand side, the positive side of the graph. Well, that's this side of the graph. We're looking at it over here. But we're looking at it from over here as we approach -1. So if you think about the graph itself, I've got so many marks on it. Let me try this again. What I'm trying to do is I'm trying to get close to the x value of -1, but I'm coming at it from the positive side of the graph. And the question you're answering is, what y value do I get close to? What does it look like? 2. I'm getting close to the y value of 2. So the limit from the right-hand side is 2. Now the second question comes at it from the left-hand side. This limit says that I'm supposed to be approaching, or I'm supposed to approach -1, but from the left-hand side of the graph. So from the left-hand side would be over here. And again, I'm still supposed to be getting close to 1, -1 rather, on the x-axis. What y value am I approaching? 1. I'm not only approaching it, I'm there the whole time, right? I mean, it's flat. So we can see from these two pieces, in one case, we never get there because it's an open circle. And if you remember, open circles mean that it's a value that we don't actually get to equal. So I do not actually get to equal it from the right-hand side. But from the left-hand side, I do. The left-hand side is actually 1. But now we got a problem. Because the third one doesn't have a plus or a minus after it. It still says -1, but it doesn't say plus or minus. So it's supposed to mean from both sides. So what happens when that graph is coming from the left-hand side down here and the right-hand side is right here, and they don't meet? It doesn't exist. So if there's a disconnect in the graph, a jump in the graph, if one limit from one side does not equal the limit from the other side, then the limit simply does not exist. Right, this is what happens if I tell my husband, meet me at McDonald's, and I go to McDonald's on Kickapoo and he goes to McDonald's on Harrison. We're not going to meet up there, right? It's going to be a problem. So this limit does not exist. Okay? Now the next two pieces are what we did in the last section. It says the limit as x approaches -infinity. Okay, so -infinity is where? Yeah, say it. The left. It's the left. If I go to the left forever on the graph, don't be on the axes, we're on the graph here, guys. So if I use what I'm given, which is to go to the left forever, what y value am I approaching? 1. Not only am I approaching it, but I actually equal it, right? It's 1. I'm there the whole time. The other one says the limit as x approaches infinity. So what happens if I approach infinity? Well, infinity is where? The right side. If I go to the right side of this graph forever, what's happening? Yeah, it's getting infinitely large. Not very fast, mind you, right? It's not doing it fast like the exponentials we looked at before, but it's still going there. So this is still going to be approaching infinity. Now, what if, this graph doesn't say this, but let me just change the graph slightly so we can have a discussion about what do I do if. What if on your graph they had drawn in a dotted line? Do you remember what happens when the people draw in dotted lines on 2, 3, 4? We'll say that that dotted line's at 4.5. What happens when your graph draws in a dotted line? What does it mean? It's an asymptote. It's telling you that something has a bound. So it wouldn't be increasing without bound. It would be bounded by that asymptote. And if this graph did that, then what would be the limit as x approached infinity? 4.5. It'd be whatever that asymptote's value is at. So just keep that in mind. That's another option of how you could see this drawn. Okay. So the directions, or the title in this section said limits and continuity. What is continuity? Well, if f is, f is continuous at a particular value x equals c, if and only if the following are true. Number 1, f of c exists. It means there is a y value. Okay, so there is an ordered pair x, y. So for this particular x value, there's a y value. The second one says that the limit exists. Okay, it's approaching something, and we know what that is. And the third one says that the limit and the function value have to be the same. So let me draw you a graph, because you might be looking at this and saying, okay, but if one of those things is true, aren't all three of them true? Because they sound very similar, don't they? They sound very similar. So let me show you a graph where maybe they're not quite so similar. So we're talking about, in this case, we'll give this function the name g of x. And we're curious about the graph in terms of continuity at 4. And we're just going to go step by step through the conditions and talk about them. The first condition says f of c exists. So when x equals 4, is there a y value on this graph that you can say, yep, when x is 4, y is something? Yes. Where is it? It's that closed circle up in the middle of the sky somewhere, right? That's the y value point. So the first condition is met. The second condition says the limit exists. So again, for the limit to exist, it must mean from both directions it's the same. So if I come at the value of 4 from the left, and I come at the value of 4 from the right, does the limit exist? Yes, and it is the open circle. It's whatever the y value is at the open circle. But everything falls apart on step 3, right? Because the closed circle, which was the y value answer on part A, if you will, and the open circle that's the y value answer on part B aren't the same. So that's not continuous. And conceptually, you knew that. You looked at this and you said, well, I know that's not continuous. And you probably said in your mind something like this, because I had to pick up my pencil to draw it. Right? Continuity has this feeling that I don't have to pick up my pencil to draw it, and I did on this one. So this one shouldn't be continuous, and it isn't, even with these directions. So let's take a look at an example, the same one that we had before. So you can flip back to page 1, or you can just look at this one. So this is on page 2 of your notes. Is f continuous at x equal 1? It says 1. So x equal to 1 is right here. Is it continuous right there? Yes, it is. The function exists. The limit exists. And they're the same. Or in more visual terms, I don't have to pick up my pencil to draw it. Of course it's continuous there. Is the function continuous at x equal negative 1? No. And visually, why not? Because what? You have to pick up your pencil because there's a jump there, right? There's a jump in the graph at negative 1 right here. The function exists. It's negative, or it's 1. The function value exists. But the limit doesn't. I mean, it just doesn't. There's no limit at negative 1. So this one falls apart sort of in step 2 of the conditions. All right, we're going to do some tables next. We had started talking about tables in the last section. We're going to continue talking about them a little bit more now. And our tables now, though, are going to approach a specific value, just like the limits are in this section, not infinity. So it says numerically estimate the limits. Show the numerical estimation tables with at least 4 estimates. Unless otherwise indicated, start plus or minus 1.1, away from the indicated or the given input value and estimate the limit to the nearest integer. Okay, so they give you lots of directions there. Almost overwhelming how many directions they just gave you. So let's take a look. This says the limit as x approaches 3 of x squared minus 9 over x minus 3. So grab your calculator, and we're going to put that equation in. Now we need to be careful when we put that equation in. Some of you have calculators that it looks like it's a numerator versus a denominator, and some of you have ones like mine where it won't. And you have to be a little bit more careful when that's the case. All right, so I'm going to put this in. In my calculator, I don't have the math type text, whatever thingy, so x squared minus 9 needs to go in parentheses. My division and my denominator, x minus 3, has to as well. So if your calculator, hang on, I didn't get my 9 in there. Here we go. If your calculator doesn't look like a fraction on top of a fraction, make sure you get those parentheses in. We're going to go into the table, and we're going to delete out what's there. That was from our last problem. And our problem says that we're supposed to approach the x value of 3. And there is not a plus or a minus after the 3, agreed? So if there's not a plus or a minus after it, what does that mean? From both sides. So we're going to create two tables. One table that's from the left and one table that's from the right. Okay? So I need to be an x value that is 0.1 away from 3, but on the left-hand side. What number is that? 2.9. So our first entry in here is going to be 2.9. And then we're going to get closer, and here's how we do it. With zeros. With nines, 2.99. And then we're going to go 2.999. And it said we had to have 4 entries, so 2.9999. And we're going to write this down. Our table will look exactly like that one that's showing up in your calculator screen right now. Have one column x, one column f of x. Our x values are 2.9, 2.99, and 2.999. One more. And we notice that our y values are 5.9, 5.99, and so forth. Your table should look like this. Does it? Okay, fantastic. But that's only from the left-hand side. Those are numbers that are slightly smaller than 3. All right, so now what? Well, we need to do the right-hand side. So we can delete these out. We need values slightly larger than 3. So what would we get if we were 0.1 slightly larger than 3? 3.1. And we're going to follow the same kind of pattern we did on the last one. In the last one we added 9s on there, right? We're not adding 9s on here because that's bigger than the number I've already done. What we're going to do is we're going to insert some zeros. So we're going to put 3.01, 3.001, and 3.0001. And all of our tables are going to feel like this. Zeros and nines. All about the zeros and the nines. We're going to write this down. Okay, very nice. And what we're wanting to do is we're wanting to look down our table and ask ourselves, what y value am I getting close to? And the answer is 6. Therefore, our approximation for our limit is that it's 6. So the notation, if you want to put it up here with this, is that the limit as x approaches 3 of x squared minus 9 over x minus 3 is actually 6. Okay, that's not too painful, right? Tedious, perhaps, but it's not painful. We can do this. Now, the next one is quite similar, and in fact, if I don't mess with my table, I might even be able to have half my table done for me once I change my equation. So, take a calculator and change your equation, but don't change your table. You can, but then people start getting confused about going down the table for what's happening. So I would encourage you to do 2 tables. Yeah. Okay. So take a look then over here. What is the only thing different about A and B? The plus, where?
X squared plus y.
All right, the numerator has a positive instead of a negative, right? Right here, there's a plus sign instead of a minus sign. It's the only thing I have to change in my equation. So if you just pressed clear and you cleared it out, you have to type it all in again. If not, all you have to do is change the sign. If you go into your table, half the table's already done. So that's cool. Because it's the same y or x value that we're approaching, 3. So this is the right-hand side of our table. So one of your sides of your table is done, or it will be when you write it down. So your x values are, again, 3.1, 3.01, 3.001. Lots more zeros, lots and lots of zeros. And now our y values on this one are quite different, actually, or our f of x. We have 186.1. We have 1,806. We have 18,006. And then 180,006. Right? And then we're going to change our table to have the 2.9s in them. So 2.9, 2.99, 2.999, and 2.9999. I have negative 174.1, negative 1794, negative 17,994. And then I have this funny number right here. It looks like 1.8E5. It's turning it into scientific notation. If I arrow over on top of it, I can get the answer on the bottom. So I have negative 17,990. Sorry, not 17,000. 179,994. You can put the decimals or not. It's not important for what we're going to be doing with it. But okay, so what happens as we go down these tables? Happening.
That one decreases, the left side decreases, and the right side increases.
All right, so first thing you might notice is the numbers don't seem to be getting close to the same thing. For one issue, one's positive, the other's negative, right? And they also seem to be getting really, really different very quickly, right? So like when I go from 17,000 to 179,000, that's a big jump, right? So on the first table, as I go down this table, this is approaching negative infinity. And as I go down this table, it's going to positive infinity. And those numbers are not the same thing. Those concepts are not the same thing, right? So this limit, what do you think we're going to say? It does not exist. Now, it's the second does not exist we've had for a very different reason. The last one did not exist because there's a jump in the graph. Do you know why this limit doesn't exist? Any idea what's happening in this graph? There's, not imaginary, there's a vertical asymptote. There's a vertical asymptote. If we were to graph this one, you would actually see, in fact, we'll do that. Oh, I just turned it off. That's not what I meant to do. Oh, for pity's sake, what did I do? Okay, so we have this equation in our calculator, and we're going to graph it. So I'm just going to do zoom 6. I didn't mean to do that. Zoom 6. And depending on how good your calculator is, will depend on whether it does this, but many of the calculators will actually put a vertical line in there because it's trying to connect the two sides and it just doesn't know what to do, so it just tries to connect them, like connect the dots, right? You know, when you're a child in Chili's or whatever, okay? Yeah, connect the dots. So it tries to connect the dots, and when it does it, it makes this vertical line. There's a vertical asymptote. So why in the world? I mean, these two equations are almost identical. It was a sign difference. One had a plus, one had a minus. Obviously, the first one didn't have an asymptote there. Do you know why?
I think the first one, the signs were the same.
The signs are different. Yes, there's an issue with the sign, and what does it do because of the issue sign? One of them, the first one, factors. And when it factors, it reduces. And when it reduces, there's no more denominator. That's what happened. So what we'll do when we meet next time is we'll finish up this lesson. I know, we didn't quite get done today. Yay for you. It's only one set of homework, right? Yeah, I know. Don't even act like you're sad. I know. Okay, but what we're going to do over here, hang on, give me just a second, okay? Just a second. Is we're going to take a look at seeing that factoring. Why in the world do some work and some not work with algebra? Okay? So we've talked about graphical limits and numerical limits, and we have one more type of limit, and that's algebraic, and we'll do that next time.